Sometimes sets are non-disjoint. And what that means is that if we have two sets, namely we'll call them A and B, they're called non-disjoint if there exist elements in their intersection. In other words, mathematically what this means is that the intersection is not equal to the empty set. So, in translation, their overlap is not empty. They do overlap. And here's a picture of what that would look like. We have A and B, and we see that this football-shaped part is what they share in common. And oftentimes what we want to do is we want to count the number of elements in their union. So if I put a few elements in here, 1, 3, 4, and maybe what they share in common is 5 and 8, and B has 17 and 22, then we can see that the union A and B, which can be formed here because they're small enough sets, would be 1, 3, 4, 5, and 8. We don't list them twice because sets do not contain duplicates. 17 and 22. And right away we can see that the size of that union is 1, 2, 3, 4, 5, 6. There's 7 elements, 7 distinct elements in total. Well, if we use the property of non-disjoint sets, if we said, well, let's just add them together, we would come up short, or, well, we'd come up too large, we'd come up with a problem. And so if we said, well, let's just add the number of elements in A to the number of elements in B, well, A by itself contains 1, 2, 3, 4, 5 elements. B contains 1, 2, 3, 4 elements. So if I listed out A contains 1, 3, 4, 5, and 8. All of those elements are members of A. B has members 5, 8, 17, and 22, and they share 2 of those elements in common, 5 and 8. So if I added together the number of elements in A, which is 5, to the number of elements in B, which is 4, I actually get 9 and not 7. I know that there's 7 unique elements that can be found when I union A and B together. So what happened? Well, if we look at what we added together all the elements that are inside of that circle A, that entire circle, ignoring B, right? Because all 5 of those elements are in A. And what we did is we added the number of elements that are in B, which is the entirety of the B circle, and we see that this portion right here was actually added in both of those totals. Those 2 elements that they have in common were counted twice. They were counted in the 5 corresponding to the number of elements in A, and they were counted again in the number of elements in B. So what we can imagine has happened here is that we double counted. We added in 1 too many times. And so if we're going to do this, if we're going to add together the number of elements in A with the number of elements in B, and we end up double counting, what we need to do is subtract away the number of elements that they have in common. On first sight, this may seem like we're removing something that we shouldn't remove, but remember, the elements in the intersection between A and B got counted twice, so if I remove them once, then I've only accounted for them 1 time. So if I take 5 plus 4, the number of elements in A, the number of elements in B, minus the double count, get 5 plus 4 minus 2, which is 7. And that leads us to a formula that we will see here, that the number of elements in the union of 2 disjoint sets A and B is the number of elements in A union B equals the number of elements in A plus the number of elements in B minus the number of elements in their intersection. Now the cool thing about this disjoint formula is that also works for, or this non-disjoint formula is that also works for disjoint sets. So let's say A and B were disjoint, And we failed to realize that, or maybe we just ignored that fact for a moment. And if now what we wanted to do was to compute the number of elements in A union B, well, and we applied the non-disjoint formula, things would still work out because we would add the number of elements in A, which is 3, the number of elements in B, which is 2, but we see that they don't overlap, and as it turns out, their intersection is empty, and so the size of A intersect B is actually 0, so I wouldn't be subtracting away anything, and you can see that all I really needed to add was the size of A with the size of B and subtract away 0, so I could have omitted that term altogether. But by keeping this term there, there's always that possibility that if they aren't disjoint, we do appropriately subtract away any double count. So now let's consider an example of a situation where we do have non-disjoint sets. Let's ask the question, how many integers between 1 and 50 are multiples of 3 or 4? So a multiple is 3, 6, 9, 12, 15, 18, and so on. And multiples of 4 would be 4, 8, 12, 16, basically counting by 4s. So we actually have a sample space here that consists of the integers from 1 to 50. Then we have the set of all numbers within S that are multiples of 3. I'll refer to those as A. We also have all of the integers between 1 and 50 that are just multiples of 4. Call that set B. Now there are some that they have in common. We know that, for example, any 3 times 4, which is 12, that's a multiple of both 3 and 4. So I can't just add up the number of multiples of 3 with the number of multiples of 4 because some of those are shared between the two. So let's think about that in terms of these sets which will have some overlap. So in set A, we'd have numbers like 3, 6, 9. And in set B, we'd have numbers like 4 and 8. But then 12 is a multiple of 3 and it's a multiple of 4. So if we kept counting, then we'd have, well, 15, 18, 21, and 24. Here we would have 16, 20. Oh, and then 24 is actually in common. Is in common between the two sets. And so that would go there. Now notice that every fourth multiple of 3 is the same as every third multiple of 4. And it wouldn't simply be that we could add up the size of A, right? So I'll list out what A is. A is the set consisting of 3, 6, 9, 12, 15, 18, 21. Oh, and this is set S up here, all of those integers. 24, 27, 30, 33, 36, 39, 42, 45, and 48. Now I should be able to count 16 elements because 48 is 16 times 3. This 3 is 1 times 3. And so whatever the largest multiplier that I can place on 3 is, that's how many elements the set has. We start counting out 1 all the way up to 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So the size of A is 16. Now B is going to be all the multiples of 4. So I have to count by 4s. 4, 8, 12, 16, 20, 24, 28, 32, 36, 40, 44, and 48. Now, we already observed that every fourth multiple of A is in common. So 12, 1, 2, 3, 24, 1, 2, 3, 36, 1, 2, 3, 48, and every third multiple of B is what A and B have in common. So 1, 2, that's 12, 1, 2 is 24, 1, 2, there's 36, and then 48. So once again, B, because 48 is going to be 12 times 4, we see that that's going to have 12 elements, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And so if I just added the size of A plus the size of B to figure out how many elements they collectively have, we'd be adding 16 plus 12, but we get all of those 4 elements that they have in common. Namely, the intersection between A and B is the elements 12, 24, 36, and 48. Look at that. Multiples of 12, right? Because that's the first number that they have in common is 3 times 4, which is 12. So every multiple of 12 will be in common between the two. So the size of their intersection is 4 elements large. And because we counted those 4 elements that they have in common within this 16 and within this 12, we need to subtract away the number of elements that they share in common to account for that double count that we have. So we get 28 minus 4 is 24. And there's our answer for that. Now, as just one extension of this, what happens if we have 3 sets? 3 non-disjoint sets, more specifically. So the picture that we can draw would be with 3 sets, all possibly overlapping. So imagine A, B, and then C will actually not only overlap with A and B, but there's going to be a portion that we'll account for that represents where all 3 of them intersect. So non-disjoint sets can be a little bit messier, especially with more than 3, because whatever you want to find the number of elements in their union, and you take this approach, if they are disjoint, then you can just add them together. The size of A plus the size of B plus the size of C. But you can see that we're counting things more than we should be. So here's what I'll do. I'll say the size of A is the size of this entire thing right here. And you see that we're counting some of the overlaps with B, with C, and with both B and C, which is this internal kind of like bullet-shaped component. Now if I did the same thing for B, B would shade everything here, and C would shade everything right here. And now let's think about how many times we counted certain things. Well, we can see that the center portion was counted 3 times. Right? That is where the green, the purple, and the orange all overlap, is in that center portion here. So this got counted in 3 times. And what is that? Well, that's the intersection of all 3. If we imagine this to be people in 3 different classes at a college, then where they all intersect represents the set of students that are enrolled in all 3 of those classes. Where only exactly 2 of them intersect, like this portion right here, those are the students only enrolled in Class A and in Class C. And we notice that that was counted in there twice, the orange and the green. So let's try this. Let's subtract away the portions where there's 1 excess overlap. So if I subtract away A intersection B, that means I'm looking at this portion right here, and I'm subtracting away one of those because the intersection between A and B gets counted twice, once in the purple and once in the green. Well, what that means is that now this center portion has only been counted in not 3 times, but 2 times, because we've subtracted away the intersection between A and B, which accounted for one of those 3 times. Now, B and C also have an overlap, right? That's this portion here. And that portion got double counted, so let me subtract away the intersection between B and C. Well, what did that do? Well, that means that that internal part where all three of them overlap is now only counted in one time. Namely, it's counted in by the intersection between A and C. Because we subtracted away all of this, we've subtracted away all of this, and now that triple intersection, A intersect B, A intersect C, is only counted in once. But the logic here is that A and C still have a double count where the orange and the green intersect. And so if I subtract that away, then I'll take away that double count. But here's the problem. Now, the triple intersection is not counted in twice, it's not counted in once. Now it's counted in 0 times because we've removed the overlaps among all the circles. So in this mathematics that we have going on here, now we have all of this, we have all of this, we have all of this, all of this, all of this, and all of this, but we didn't account for the intersection between A and B and C because we subtracted away 3 separate overlaps between 2 pairwise sets. So because it's not accounted for at all, we need to add it back in. So we would add in the intersection between A and B and C because it was originally counted 3 times, but because we started off by subtracting away the overlaps between any 2 of them, we have completely removed it from the count, and now we're going to count it back in. So you can see that this formula gets quite a bit more involved than for non-disjoint sets involving only A and B.